Now let us go over different important properties of hyperbola and its tangent and normal. So let us start by the first property. It says that the difference of focal lengths for any point on the hyperbola is always constant. If you recollect, this is one of the hyperbola itself. That is, if you consider a hyperbola, let's consider it in a standard form, and we show the two foci. Let's call them as S and S dash. Okay. Let's consider any point on the hyperbola, that is P. Okay. So therefore the focal distances are PS and PS dash. So the difference of these two focal distances is always constant for any hyperbola, and in fact that is nothing but 2 times A, where we know that 2A is the length of the transverse axis of the hyperbola. So that's the first property, which is a defining characteristic. Moving on, the locus of feet of perpendiculars drawn from foci to any tangent of hyperbola is its auxiliary circle, and the product of lengths of these perpendiculars on any tangent is B square, that is the square of semi-conjugate axis. So let's understand what does this mean. This is a hyperbola. Suppose we consider some tangent to it, and these are the foci. Okay. If you drop the perpendiculars, from the two foci to this particular tangent, and suppose we note where are their feet of perpendiculars, like this. Now we can do this for all the possible tangents to the hyperbola. We will observe that all these feet of perpendiculars basically form nothing but the auxiliary circle. So therefore the locus of all these feet is the auxiliary circle of the hyperbola. Here it's not on the scale, but it is the auxiliary circle. And the product of lengths of these perpendiculars, so this is let's call this as, say, L1, the length of first perpendicular, that is from one focus, and let's call the other as L2. Okay, so the product of L1 and L2 is always equal to B square for any tangent. And here in this case, since I have shown the hyperbola in the standard horizontal manner, the B basically means it's the semi-conjugate axis, that is half of the length of the conjugate axis. Moving on to the next one. Tangents drawn at endpoints of latus rectum of hyperbola pass through the foot of the corresponding directrix on transverse axis. So here also let us first draw the hyperbola. Okay, you know that the directrix will be located inside, that is towards the y-axis, like this. Now let's consider the latus rectum, something like this. Latus rectum is a segment that is perpendicular to the transverse axis, and let it cut the branch at LL dash. Now here if you draw a tangent to the latus rectum, it will pass through the point where the directrix cuts the transverse axis. Okay, so both the tangents, that is the tangents drawn at the endpoints of the latus rectum, will pass through the same point where directrix cuts the transverse axis. And it's true for the other latus rectum also. So in other case, they also will pass through the point where the other directrix cuts the transverse axis. Now this property is exactly same in case of the ellipse also. Alright, let's go ahead. The part of the tangent between the point of contact and the point where it meets the directrix subtends right angle at the corresponding focus. Okay, now this is also very much similar to what we have in case of ellipse. Let us show the directrix in blue, something like this. Okay. Here I consider some tangent drawn to the ellipse, sorry, to the hyperbola. Okay. Then let us show the point where it cuts the directrix. Let us call that as point Q, and the point at which the tangent is drawn, let us call that as point P. Alright. And here I have the focus, that is S. Okay. Now, if you join QS and PS, it will be a right angle. Right? That is what this property is saying. So the part of the tangent which is PQ, that's the part where it lies between the point of contact and where it cuts the directrix. Now this particular segment PQ subtends a right angle at the respective focus. Let's go ahead. Now here this is another interesting property, again similar to the ellipse, that is a reflective property. Now before we actually see what is the reflective property, we have to understand one fact first, that is the tangent and normal at any point on a hyperbola bisect the angles between the lines containing its focal radii. So by the word its means of the points. Okay? So let's see what this means. Once again I draw a standard hyperbola. Okay, tangent and normal at any point on a hyperbola. Okay, so let's consider any point. So let me show some point here, say P. Let us draw a tangent here. Again, this is not to the scale, it's only for understanding purpose. Now we have two foci, show them as S and S dash. Okay. Now let us join the foci with that point. So that gives us the line containing the focal radius S dash P. Similarly, we can join P with S also, and of course extend it. That will give us another line that contains the focal radius SP. Now at the point P, let us also draw the tangent, the normal, that is a line which is perpendicular to the tangent that we have already drawn. Now what this property is saying is the tangent and normal both at that point bisect the angle between the focal radii. So if you see the angle between the first focal radius S dash P and the tangent, so this is the tangent, is same as the angle between the second focal radius and the same tangent. Similarly, the angle between the first focal radius, say S dash P, and the normal is same as the angle between the second focal radius, that is SP, and the same normal. Okay, so in this way the tangent as well as normal both are the angle bisectors between the lines containing focal radii. Now we use this fact to understand this property in some other way. Okay, that is, now in place of these lines, suppose we consider some light source. Okay, if we keep the light source at a focus, we get the next important result, that is a light ray directed at one focus gets reflected from the hyperbola towards the other focus. So let's once again understand what is the meaning of this. Suppose we have a hyperbola, it is its axis, this is the focus S and this is another focus S dash. Now suppose there is one ray that is coming towards one focus, say S. Now since this ray gets reflected from the hyperbola, think of the hyperbola as if it's a mirror, it's a convex shape of mirror. When it gets reflected, it will get reflected in the direction of the second focus. That is what is the meaning of this property. Simply because if you remember from the ray optics, to find out the direction of the reflected ray, we first of all draw the tangent to that particular point of incidence and then we draw the normal. Okay, and we know that angle of incidence is same as angle of reflection. So therefore We have seen the property that tangent and normal bisect the angles between two focal radii. Therefore, clearly the light ray which is aimed at one focus on reflection gets directed towards the other focus. That's the reflective property of the hyperbola. Let's move on to the next property. No normal of the hyperbola apart from the transverse axis passes through the focus of the hyperbola. So this is also very much similar to ellipse. That means the only normal of the hyperbola that passes through the focus, or rather both the foci, is its transverse axis. You can see that the transverse axis is a normal to the hyperbola at the vertices, that is A and A dash. At all other points, when you draw the normal, this particular normal will never pass through any of the foci.